ugly. And I'll just put that there just to show you. You go to the Wikipedia thing too. I will not force you to do any of this kind of stuff.
What's ugly about that?
It can be fun, but it's not straightforward. But
Doesn't look bad.
it isn't. It's linear algebra.
It's just matrices and whatnot.
Yeah. So if you ever want to do this math, take a class in linear algebra and you can do everything. But without linear algebra, you kind of struggle a little.
It's also Cal 3, isn't it?
What's that?
No.
Oh, a little bit, not much.
They
We touch on it, but
give
not
you
a lot.
an intro to matrices in Cal 3, but it's not.
But if you take a linear algebra class, you could do that math in 5 minutes. We don't worry about it here. Last thing I want to do before we finish this particular topic is sort of an aside that relates, that's a geologic characteristic that relates to the discussion we've been talking about so far. In the terms of kinematics, we talked about translations and rotations, and then we talked about distortions, which give rise to this concept of strain. I talked about heterogeneous strain, or heterogeneous deformation versus homogeneous deformation. That concept, and this concept of finite strain that we've been talking about, can be extended to a problem that we have to worry about in geology, that I'll beat in your head over and over in this class, is that scale is a problem. It has to be considered in how you analyze a problem, a structural problem that deals with a full kinematic system that has strain, rotations, translations, and the like. And what that comes down to is, and it relates to this, and that's why I'm doing this now, is that you can imagine a range of scales across which a material gets deformed. So let's take a hypothetical characterization of this. From thin section scale to, here's a small scale of that. You look at different scales of this particular object. This is an undeformed material, right? And you look at that material at different scales. There are different ways of viewing that depending on what scale you're looking at. When you look at it at that scale, which is up there maybe at map scale, and this is what a geophysicist would look at as the physical properties of something you might measure, right, of an igneous rock. The material, that material looks totally homogeneous to you because the anisotropy in the material, which is made up of the crystals, averages out. So if you were to measure the physical properties in this direction, that direction, that direction, you're going to look the same because you average out the heterogeneity of the crystals. If you zoom down and scale them, you're going to reach the stage where if you measure the physical properties, you're starting to measure the physical properties of individual crystals, and you would call that anisotropic at that scale. Or if you scale that up at some slightly larger scale, I don't know why this got shown on that particular scale, it just averages out even more and it disappears, right? Any kind of anisotropy of the crystals, like triclinic crystals, right? Very anisotropic material, or something that has very high birefringence, right? Crystal, it has high birefringence, it's very anisotropic in terms of its physical properties. Now, if you take that material and you align it, which is what strain does, and you take those objects and change their shape, now you've produced an alignment of materials. This is what we call fabric, is the alignment of the anisotropy that makes up the material. So you take these objects and you line them up. Now you've got a problem that relates to a range of scales in which you can describe this problem. If you're at a scale, let's take sort of this intermediate scale. At this scale, the material is behaving. There's homogeneous. The rock is homogeneous in the sense that at that scale, there are the objects that make up the material are aligned in this direction and not in this direction. But straight lines are straight lines. There aren't a lot of curved lines within that system. So at this scale, the system can be treated as a strain problem because the objects start out with straight lines, end up with straight lines. And you can scale that down through a range of scales until you start getting, in this particular case, to the grain scale. But once you get to the grain scale, if you start zooming in at this level, it'll be like this. It'll start to disappear on you. So there's a minimum level at which you could treat the problem as a strain problem. At this stage, it's a discontinuum, if you will. It's not a continuous material. There's grains and distinct grains, and you can't sort them out. Correspondingly, if you scale upwards from this to this, suddenly your nice straight lines get curved, right? You got folds, or even more so, go to this, and you got larger scale curvature within the problem. Now you're no longer in homogeneous distortion at that scale, you're at heterogeneous distortion. So there's an upper scale in which you no longer have straight lines. This could still be treated as a deformation problem because you've got curved lines, but the problem increases in complexity at this level because it's heterogeneous deformation. Whereas strain can be estimated at this level. You can't estimate strain here without knowing strain there, there, and there, and other things that would define the problem. Because you have a rotation and a strain and things like that would be required to describe the problem. It's because of that one of the things you have to learn in working with any rocks that have distortions within them is your mind has to twist around to thinking about these two different thresholds, a lower threshold below which you can't think of it as a strain problem, and an upper threshold in which you can't think of it as a simple strain problem, but a heterogeneous deformation problem. But there's always some scale in which you can, analyze the problem. You might not be able to make quantitative assessments, but you could be able to do that. Here's just a couple of random field photographs that illustrate examples of systems that have object shapes that are illustrating that kind of an effect, or a range of, at these scales on these systems. This is a large scale. You got a pen for, there's a pen for scale in both of those. These are objects that are distorted, and at that scale, the material is homogeneous. So you could measure these object shapes, and you could use that to estimate the finite strain within the material. You could plot those on a Flynn diagram. In fact, these came from near one of those photographs. I can't remember what that one is. That one's harder to see. And it's actually true of this one as well. But this one, I should have brought something else. Look at this system. The layers in this rock are looping all over the place. That's about the same size as that pen. Now this problem is such that there's curvature down to this side of scale. So you can only look at this as distortions at these tiny, tiny scales. Everything is heterogeneous above that scale. I guess I could extend that over here too. If you got down to this scale right there, you wouldn't see those features either. So that's the minimum threshold to see the object shapes that would make up that particular feature. So the point is, their scale is an important problem, an important thing to deal with when we look at problems of strain. The strain has a range over which that's a quantity that has meaning. When you go above it, you have to deal with other issues. When you go below it, you can't even estimate it. And I didn't skip that one. And so just a sort of summary of that particular concept. I'll come back to penetrative later, but there's this minimum versus maximum scale. Below the minimum threshold, it can't be described as a strain problem. You have displacements and rotations, but you wouldn't be able to describe it as a strain. But above a certain level, it's not a strain problem either, because then it's heterogeneous distortion. I think that's the end of that particular set. And okay, let me think whether it's worth